I want you to picture a scene. It's early Tuesday morning. You're the owner of a medium-sized manufacturing plant in Maharashtra.
Right.
You make stamped steel auto parts. And the factory floor out there is just deafening. You've got mechanical presses slamming down, conveyors running, induction motors screaming.
Oh, yeah, it's a symphony of heavy industry out there.
Exactly. And you are sitting in your cramped cinder block office, drinking a lukewarm cup of chai, staring at a piece of paper that is just, well, it's completely ruining your week.
The monthly electricity bill.
A monthly electricity bill. But you aren't just looking at the cost of the power you use to stamp those steel parts. You're looking at a separate line item at the bottom, a penalty charge.
Yeah.
A massive punitive fine levied by the utility company, just bleeding away whatever razor-thin profit margin you managed to scrape together this month.
And, the most frustrating part is this isn't a new problem for you. You actually tried to fix this.
That is the most agonizing part. You look out the window of your office down onto the factory floor, and sitting right there against the far wall is this massive battleship gray metal cabinet, an industrial electrical panel.
Right, the APFC panel.
Yeah, and you spent lakhs of rupees on that cabinet just 2 years ago. The vendor who sold it to you stood in this exact office, shook your hand, and promised you that this expensive piece of hardware was explicitly designed to eradicate those utility penalties forever.
And for the first few months, it probably did.
It did. The fines vanished. You thought the problem was completely solved. But now you're looking at the bill, and the exact same penalties have quietly crept back in. The cabinet hasn't moved. It hasn't been hit by a forklift. It's humming away. Its little indicator lights are blinking. I mean, it looks entirely functional. Yet you are being fined as if it doesn't even exist.
Yeah, you are looking at the absolute definition of an invisible bottleneck. And it's a phenomenon that is quietly devastating the MSME sector. Micro, small, and medium enterprises. It is a massive profit leak happening right in plain sight.
Well, welcome to this deep dive. We have a highly specific, custom-tailored mission for you today. Okay, let's unpack this. We are going to figure out exactly why that expensive gray box is failing, why the utility company is suddenly so aggressive about these fines, and how an entirely new class of technology is swooping in to fix it.
It's quite a story.
It really is. And to figure out what is going on, we have a fascinating stack of sources on the table today. We're looking at a highly detailed analytical report published in Boiler World Update.
Right, authored by C.A. Mahavir Kumar.
Yes, exactly, which completely dissects high-tension consumer data across Maharashtra. We've also got the actual official tariff circulars from MSEDCL, that's the Maharashtra State Electricity Distribution Company Limited, and we're pulling from some incredibly sharp strategic notes on restorative engineering, edge AI monetization, and the physics of industrial power.
We are dissecting a perfect silent collision of regulatory policy, inevitable mechanical failure, and software innovation.
Yeah.
And what's fascinating here is that the core problem isn't a sudden surge in the factory's production.
Yeah.
And it isn't even the electricity itself. The fundamental bottleneck is a regulatory shift from what the industry calls kVAh billing to kVAh billing. And that single bureaucratic shift completely exposes a systemic failure in how industrial hardware is sold and maintained.
I want to spend a lot of time on that regulatory trap because, you can't understand the solution until you intimately understand the physics of the problem.
Absolutely.
So let's wind the clock back to April 2020. This is when the utility board, MSEDCL, made a change that effectively turned the entire billing system upside down for industrial consumers. To understand what they did, we have to talk about how electricity actually behaves when it hits a heavy machine.
Right, we have to define the nature of the power being drawn from the grid. Technically speaking, when an industrial facility turns on its machines, it's drawing two distinct components of electrical power, active power and reactive power.
Okay, active power is the straightforward one.
Right? Yeah, it is, yeah. Active power is the actual usable energy that performs the physical work. It's the energy that physically spins the heavy steel shaft of the induction motor.
Okay.
It heats the massive industrial ovens. It drives the conveyor belts forward. It's measured in kilowatts. and over time, kilowatt hours or kilowatt hour.
Yes.
So if you turn on a traditional incandescent light bulb, you're using almost entirely active power to create that heat and light.
But heavy industry isn't just a bunch of light bulbs. It relies on alternating current and heavy induction motors. And that introduces the ghost in the machine.
Reactive power.
Right. So explain the physics of reactive power to me, because it is notoriously difficult to visualize. I mean, why does a motor draw power that doesn't actually do any work?
Because of magnetic fields. Almost all heavy industrial machinery relies on induction motors and transformers, which operate on alternating current.
Okay.
For an induction motor to physically spin, it first has to generate a massive, rotating magnetic field inside its iron core. That magnetic field is the invisible bridge that transfers the electrical energy into mechanical rotation. Got it. But creating and sustaining that magnetic field requires a constant surging of energy back and forth between the power grid and the motor.
So it's just sloshing back and forth.
Exactly. It flows from the grid to the motor to build the magnetic field, and then as the alternating current wave reverses, that energy flows right back out of the motor and back onto the grid. It surges back and forth 50 or 60 times a second, depending on your grid frequency.
Wow.
And this oscillating energy doesn't perform any of the mechanical work, like it doesn't stamp the steel part, but it is absolutely physically necessary for the equipment to function. Without the magnetic field, the motor is just a dead lump of iron. This sloshing energy is measured in kilovolt amperes reactive, or kVAh.
I was trying to think of a good way to visualize this earlier. You know, you often hear people use the analogy of a beer glass.
Ah, the beer and foam analogy. Yeah, it's practically mandatory in electrical engineering textbooks.
I know. Where the active power is the liquid beer you actually want to drink, the reactive power is the useless foam at the top, and the apparent power is the total volume of the glass.
Right.
But I actually really dislike that analogy.
Oh, really? Why is that?
Because it fails the mechanistic test. I mean, in a beer, the foam is just a useless byproduct of pouring it badly. You don't need the foam to drink the beer. But as you just explained, a factory absolutely needs reactive power to build the magnetic field.
That's true.
Without it, the machines won't turn. It's not a useless byproduct. It's a structural requirement. So I want to try a different analogy. Imagine a horse pulling a heavy canal boat.
A canal boat. Okay, let's explore this.
So you have a deep canal and a heavy wooden boat full of cargo. But the horse pulling the boat can't walk on water. The horse has to walk on the towpath, you know, the dirt road running alongside the canal.
Right, on the bank.
Exactly. The horse is attached to the front of the boat by a long rope. Now, the horse starts walking forward. It is expending energy.
And the total energy the horse is expending is the apparent power, the kVAh.
Exactly. Now, because the horse is on the side of the canal, the rope is pulling at an angle. The energy the horse exerts has two effects. The most important effect is that it pulls the boat forward toward its destination. That forward motion is our active power, the kVAh. It's the actual useful work being done.
But because of the angle of the rope, the horse is also pulling the boat sideways towards the shore.
Yes, the boat wants to crash into the bank. To stop this, the person steering the boat has to shove the rudder hard in the opposite direction to keep the boat pointing straight. The energy the horse spends pulling the boat sideways against the resistance of the rudder, that is our reactive power, the kVAh.
That is a much more accurate visualization. Because the sideways pull doesn't move the boat toward its destination, but because the horse is physically constrained to the towpath, just as an induction motor is physically constrained by the laws of electromagnetism, that sideways pull is unavoidable. You can't get the forward motion without dealing with the sideways force.
Right. And here is where the utility company, MSEDCL, enters the picture.
Think about the utility as the farmer who owns the horse.
Okay.
Historically, the farmer would look at the boat, see how far it traveled down the canal, and bill you for the forward motion. They billed you for the active power, the kilowatt.
Which makes perfect sense to the factory owner. You pay for the steel parts you successfully stamped. You pay for the forward progress.
But the utility company has a major headache. Even though they are only billing you for the forward motion, they still have to feed the horse enough oats to cover the total effort, including the wasted sideways pull.
Yes, and on a grid level, that's a massive physical burden. The grid has to physically generate and transmit all that reactive power. That sloshing energy takes up physical capacity on their transmission lines. It heats up their massive neighborhood transformers.
Oh, wow.
Yeah, it causes systemic voltage drops across the entire city grid. If every factory in Maharashtra is drawing massive amounts of reactive power, the utility has to build thicker cables and bigger power plants just to handle the sideways pull. So, To force factories to be efficient, utilities introduced the concept of the power factor. Power factor is simply the ratio of the useful forward work to the total effort. It's the ratio of active power to apparent power.
Right. If your horse is walking on a tow path that is very close to the boat, the angle is small, the sideways pull is minimal, and your power factor is very high, close to a perfect 1.0.
But if your factory is full of old, inefficient, highly inductive motors, it's like the horse is walking far away in a distant field, pulling at a massive angle. The power factor drops drastically. Maybe it hits 0.8 or 0.7.
And under the old historical billing system, utilities tried to manage this with a carrot and stick approach based on that ratio. If you kept your power factor pristine, say 0.98 or 0.998, they would give you a power factor credit.
Nice.
They essentially said, thank you for making our grid run cooler and our transmission lines more efficient. Here's a 1% or 2% discount on your monthly bill.
But if you were terrible at it, and your power factor dropped down to 0.85, they would hit you with a penalty surcharge on top of your regular kilowatt bill to cover their transmission losses.
Which brings us back to April 2020. MSEDCL looked at the grid, looked at their losses, and decided the carrot and stick approach wasn't enough. They changed the fundamental architecture of the tariff. They stopped billing for the forward motion entirely.
Wow.
Yeah, they shifted the entire billing structure from kilowatt rup to kVAh, kilovolt ampere hours.
So they decided to stop billing for the distance the boat traveled and just started billing for the total physical exhaustion of the horse.
Precisely. The utility simply says, we don't care how much useful work you got done. We're going to put a meter on the total apparent power you draw from our grid, the vector sum of both active and reactive power, and you will pay for every single drop of it.
I was looking at the official MSEDCL tariff circular you brought, and the math of how they implemented this shift is absolutely brutal. I mean, I don't want to just read out algebra on audio, but the geometry of the new formula is crucial to understand why factories are suddenly bleeding cash.
Let's walk through the geometry. To calculate the total apparent power under the old system, they basically used the Pythagorean theorem. You take the active power squared, add the reactive power squared, and find the square root of that sum.
But the new 2020 kVAh billing formula makes a critical announcement regarding the types of reactive power. Because reactive power isn't just a monolithic thing, right?
Right. Reactive power can be categorized as either lagging or leading. When a factory runs a heavy induction motor, the magnetic fields cause the current wave to literally lag behind the voltage wave in time. This creates lagging reactive power. This is the horse pulling the boat to the left.
But you can also have things that push it to the right.
Yes. Capacitive loads, like the capacitor banks we'll talk about shortly, do the exact opposite. They cause the current to lead the voltage. This creates leading reactive power.
Now, under the old kilowatt system, if a factory had a bunch of lagging reactive power from their motors and a bunch of leading reactive power from their capacitors, the utilities formula sometimes allowed those opposing forces to effectively cancel each other out in the grand calculation, or the utility would only strictly penalize the lagging portion.
But the new 2020 kVAh formula makes a ruthless mathematical change. It explicitly takes the leading reactive power and adds it to the lagging reactive power before squaring them.
Wait, let me make sure I have the geometry right. It adds them together. It doesn't net them out.
It adds their absolute values together. It treats them both as structural inefficiencies that burden the grid. So, whether your horse is pulling the boat violently to the left or violently to the right, the utility considers it all wasted effort. Any deviation from pure forward efficiency in any direction compounds your total apparent power bubble.
That is a staggering shift. I mean, if you overcorrect, you get penalized just as hard as if you undercorrect. So what does this all mean for the factory owner just trying to keep the lights on? Let's put some real-world numbers to this, because the analytical report from Boiler World Update has a specific case study that makes the financial damage crystal clear.
I'm looking at the Mahavir Kumar report here,
Yep.
and this example perfectly isolates the impact of the rule change. Let's imagine a factory that draws exactly 10,000 units of active power, 10,000 kilowatters. They have heavy motors, so they generate 1,500 units of lagging reactive power.
All right.
But they also have some capacitive equipment, generating 3,500 units of leading reactive power.
Okay, so under the old system, the utility does the math, and they calculate the factory's power factor at 0.981. That is a fantastic score. The horse is pulling almost dead straight. In fact, it's so good that the utility awards the factory a 1.5% incentive credit. They are billed for exactly 10,000 units, and they get a discount. The factory owner is thrilled.
Now, the calendar flips to April 2020. The factory hasn't changed a single thing. They are manufacturing the exact same products, running the exact same shifts, on the exact same machines. They're still drawing the exact same 10,000 units of actual work. What happens to their bill under the new MSE-DCL kVAh formula?
Under the new formula, the utility adds that 3,500 leading power and 1,500 lagging power together. That gives you 5,000 total units of reactive inefficiency. When you plug that massive number into the new apparent power equation, the total billed units violently spike from 10,000 to 11,180.
And their calculated power factor plummets from a pristine 0.981 down to a dismal 0.894.
So practically speaking, the factory's electricity bill just increased by 11.80% overnight, without them turning on a single extra light bulb.
And we must ground that number in reality. For a manufacturing facility, electricity is not a secondary expense. It is often their second or third largest operational cost, right behind raw materials and payroll. An 11.8% spike on a bill that might already be 15 or 20 lakhs a month is a devastating blow. It completely wipes out the profit margin on the goods they're producing.
And it doesn't stop there, does it? Because
Right.
MSE-DCL doesn't just quietly bill you for the larger apparent power bubble. If your power factor drops too low, they actively hit you with those punitive fines we talked about at the beginning.
Exactly. The tariff order outlines a very strict cascading penalty structure. The moment your average monthly power factor drops below 0.90, the penalties activate. At 0.89, they slap a 1% penalty on your entire bill, excluding taxes.
Wow.
If you drop to 0.85, it's a 3% penalty. By the time you hit 0.82, you're facing a 4.5% punitive surcharge on your entire energy consumption.
And conversely, if you manage to thread the needle and keep your power factor perfectly balanced between 0.95 and a perfect 1.00, they will still offer you incentives up to a 3.5% reduction. So the total arbitrage gap between suffering a steep penalty and earning the maximum incentive is massive. We're talking about an 8% or 9% swing in total operational power costs.
So the regulatory trap has been perfectly set. The fines are suddenly bleeding these factory floors dry. And naturally, the free market responds. Factory owners realize they have a catastrophic new expense on their hands, and they look for a solution to plug the leak.
Which brings us to the tragedy of the expensive gray metal box. The market solution to this new kVAh billing reality was to sell MSMEs a piece of hardware called an APFC panel, automatic power factor control.
When the MSE-DCL tariff officially shifted in 2020, there was an absolute gold rush. Industrial consumers scrambled to purchase these APFC panels. It was viewed as the silver bullet.
Let's break down what this panel actually does, mechanically speaking. If the factory's induction motors are the problem because they drag the current behind the voltage, how does the APFC panel fight back?
The APFC panel fights back by artificially injecting the exact opposite force. Inside that massive gray cabinet are rows and rows of industrial capacitor banks. While an induction motor creates lagging reactive power, a capacitor creates leading reactive power.
So if the motor is pulling the canal boat hard to the left, the capacitor is a rudder pushing the boat hard to the right.
Precisely. A properly designed APFC panel has a microprocessor inside it. It monitors the real-time electrical load of the factory. If a massive stamping press cycles on, drawing a huge wave of lagging reactive power, the panel instantly senses it. The microprocessor triggers mechanical contactors, which slam shut and connect specific capacitor banks to the factory's internal grid.
Oh, I see.
It injects a precisely calculated wave of leading reactive power to perfectly neutralize the lag. The two opposing forces cancel each other out internally, and what the utility company sees from the outside meter is a perfectly efficient factory drawing pure active power.
A perfect 1.0 power factor. The boat goes perfectly straight down the canal. So the factory owner spends hundreds of thousands of rupees buying this sophisticated piece of engineering. They install it, the utility fines vanish, they breathe a sigh of relief. But then, as we established in our opening scenario, 2 years later, the fines come roaring back. The panel failed. Why?
Because of the deeply flawed business model of the incumbent hardware vendors. The Boiler World Update analysis explicitly diagnoses this as the sell and disappear approach.
Sell and disappear.
Yeah. These traditional electrical vendors operate purely on a point-of-sale transaction model. Their entire incentive structure is designed around selling the factory owner a heavy metal box, securing the final invoice payment, and moving on to the next client.
They aren't energy partners, they're box pushers.
Entirely. And this creates a cascade of terrible technical decisions. The report highlights the absurdly shallow sales practices used by these vendors. First and foremost, vendors frequently quote and size these massive APFC systems based on reviewing a single latest electricity bill from the consumer.
I was reading that and it blew my mind. A factory is an incredibly dynamic environment. The electrical load fluctuates wildly depending on the season, the production shift, the specific raw materials they're processing that day. A textile mill in July runs fundamentally different electrical loads than it does in December. You cannot possibly design a permanent, highly sensitive hardware fix based on a static 30-day snapshot of a utility bill.
It's engineering malpractice. But it gets worse. The vendors provide these quotations without any detailed technical design specifications. They just hand the factory owner a one-line quote that says, supply and installation of APFC panel, 210 kVAh capacity.
That's it.
That's it. There is no careful selection of specific capacitor types by electrical engineers who actually understand the specific harmonic distortion environment of that particular factory floor.
So the MSME owner, who's already stressed about cash flow, looks at 3 different vendor quotes. They all just say 210 kVAh panel. Naturally, they negotiate purely on cost. They buy the cheapest gray box.
And the vendor installs it. And to be fair, the vendor's engineers ensure it works for the first 1 to 3 months, because that is the critical window where they demonstrate a good power factor to the client, prove the fines have stopped, and get their final project sign-off and payment. But the moment that check clears, the vendor vanishes.
And they leave the factory owner completely blind to the inevitable mechanical reality playing out inside that cabinet.
Let's deep dive into the physics of why that gray box eventually dies, because it is fascinating. The strategic notes on restorative engineering make a very clear point. Capacitors are not permanent structural elements. They are consumable components.
This is the crux of the failure. People look at heavy industrial electrical equipment and assume it is robust, like a steel beam. But capacitors are fundamentally consumable. They wear out. They degrade.
Explain the physics of that degradation to me. What is actually breaking inside? To understand the breakdown, you have to look at how a capacitor was built. Internally, an industrial capacitor consists of massive sheets of conductive metal foil, tightly wound together, separated by incredibly thin layers of dielectric material, usually a specialized polypropylene film.
Okay.
This dielectric film is the insulator. It is what allows the capacitor to store its electrical charge.
Okay, so metal plates separated by ultra-thin plastic film.
Now, subject that delicate internal structure to a heavy industrial environment. Every single time a machine on the factory floor turns on, the APFC panel recognizes the lag and violently slams its contactors shut to bring the capacitor online. The moment that happens, a massive rush of electrical current, known as an inrush current, hits the capacitor. This creates intense, localized thermal and electrical stress.
It's essentially getting hit with a tiny lightning bolt every few minutes.
Yes. Over thousands and thousands of switching cycles, the extreme voltage peaks and the heat begin to physically degrade that dielectric polypropylene film. The material experiences microscopic breakdowns. Tiny little electrical arcs punch through the film.
Wow.
The internal pressure of the cylinder increases. And as that dielectric material physically breaks down, the capacitor undergoes what engineers call deration. It loses its ability to store and inject a charge.
It loses its capacitance.
Exactly.
Yeah.
A capacitor bank that was rated by the factory to deliver 25 kVAh of leading reactive power on day 1 might only be physically capable of delivering 18 kVAh a year later. 2 years later, it might be down to 12.
Okay, this is where the blind spot becomes lethal, because the vendor is gone and the APFC panel's internal microprocessor doesn't actually measure the health of its own capacitors. The panel's logic board says, I detect a massive motor turning on. I need 25 units of correction. I will close the relay for capacitor bank number 3.
Right.
The panel thinks it has solved the problem. It assumes bank 3 is still delivering 25 units.
But bank 3 has suffered heavy thermal degradation. It's only delivering 12 units. So the panel fails to properly correct the power factor. The lag isn't neutralized. The total apparent power bubble swells. The utility meter mounted on the outside of the factory, which is highly accurate, instantly registers the drop in efficiency, and the penalty seamlessly returns to the monthly bill.
Now, I have to push back here and put myself in the shoes of the factory owner again. If I am running a business and my electricity bill suddenly spikes with a penalty, why don't I just walk down to the electrical room, open the panel, look at the capacitor, realize it's broken, and order a replacement part? I mean, it's just a broken part. Why let the fines stack up for months?
Because it is impossible to see. A degraded capacitor looks physically identical to a healthy capacitor. There are no warning lights in the individual cylinders. The panel itself usually has a cheap, basic display on the front door that often defaults to showing the target power factor it thinks it is achieving, not the reality of the degradation.
And this highlights the massive systemic externalization of risk that the vendors get away with.
Completely. The incumbent hardware vendor takes the upfront capital profit from the sale, but they externalize the entire multi-year risk of component degradation onto a factory owner who is structurally completely unequipped to monitor it.
The MSME owner is probably handling sales, managing HR disputes, negotiating raw material sourcing, and sweating over payroll all at the same time. They know how to repair a jammed hydraulic press because it's a visible mechanical problem.
Right.
But they do not have a dedicated electrical engineering team on staff to track complex logarithmic degradation curves of dielectric film inside a sealed box. They just see a bill, they assume a utility raised rates, or they assume electricity is just getting more expensive globally. They lack the diagnostic legibility to realize that a single $50 component has lost 30% of its capacitance.
If we connect this to the bigger picture, it's a systemic failure where vendors externalize the risk onto factories that lack the resources to monitor it. And the vendor knows this. The vendor knows the physics dictate the hardware will inevitably degrade, but the point-of-sale business model provides zero financial incentive for them to care what happens in year 2.
All right, so we've established the regulatory trap, and we've thoroughly diagnosed the vendor failure and the physics of the hardware breakdown. Now I want to shift gears and look at the hard data, because this isn't just an abstract theory about thermodynamics. We have real numbers. The report published by CA Mahavir Kumar actually crunched the MSEDCL billing data for high-tension consumers over an 11-month period, from January 2021 to November 2021. This gives us a massive empirical data set to see exactly how much money these MSMEs are bleeding.
The data paints a very grim picture. Let's establish the scope of the analysis first. The report intentionally excluded the smallest industrial consumers, those with a contract demand of less than 200 kVA. That filtered out about 34% of the total, allowing the analysis to focus on the serious, heavy industrial users.
And of the remaining high-tension consumers, where does the bulk of the market sit?
A staggering 95% of those remaining consumers fall into the 200 kVA to 2000 kVA load range.
Okay, 200 to 2000 kVA. What does that actually look like in the real world?
That is the absolute heart of the MSME sector. The mid-sized textile mills, the plastic injection molding facilities, the regional cold storage warehouses, the auto component manufacturers. These are the factories that literally form the bedrock of the industrial supply chain.
And we must remember the timeline context of this data. This is 2021. The report explicitly notes that this sector was emerging from the catastrophic repeated lockdowns of the COVID-19 pandemic. These MSME units were dealing with shattered supply chains, fluctuating demand, and immense financial fragility. Margins were already pushed to the absolute brink.
In that environment, optimizing a major operational expense like power is not just a best practice. It is frequently the difference between surviving and liquidating.
But the data set reveals they are utterly failing to optimize it. There is a statistic in the Boiler World update that I had to read 3 times to believe. Of all the consumers in that crucial 200 kVA and above range, 25% of them, 1 out of every 4 factories in the state, have an average power factor of less than 0.90.
They're living permanently in the penalty zone.
And it gets so much worse. If you isolate that bottom 25%, the bottom quartile, and look at their specific performance, the average of their average power factor is a dismal 0.766.
0.766.
Let's translate that back to our canal boat analogy. If 1.0 is the horse pulling perfectly straight and 0.9 is pulling at a slight angle, a 0.766 means the horse is basically trying to drag the boat sideways onto the shore. It is an astronomical level of system inefficiency. They are paying for an enormous apparent power bubble that is doing absolutely no work.
When you plug a 0.766 power factor back into the kVA billing formula we discussed earlier, the financial implications are staggering. The report calculates that at that level of inefficiency, these MSMEs have the scope to reduce their total power cost by over 25%.
Stop right there. A 25% reduction in their largest operational expense. Think about what that actually means for a stressed MSME owner. We aren't talking about abstract accounting numbers. If your power bill is 20 lakhs a month, a 25% reduction is 5 lakhs saved every single month. That is the payroll for an entire shift of workers. That is the capital needed to survive a sudden spike in the cost of raw steel. That is the margin that keeps the factory doors open.
And what makes it so tragic is that the report explicitly notes that fixing this specific power factor issue would yield a total recovery of the intervention cost within 6 to 12 months.
A 6 to 12-month return on investment is practically unheard of in standard industrial capital expenditures. If you buy a new high-efficiency CNC machine, you are thrilled if it pays for itself in 3 to 5 years. If you can get a 6-month ROI on fixing your electrical panel, why isn't every factory owner in the country doing it instantly?
Because they can't see the leak. The barrier isn't the cost of the replacement capacitors. The barrier is the total lack of legibility we've been talking about. They don't know the problem's mechanical. They just think electricity is expensive.
Now, I have to ask a skeptical question here. Looking at this data, it's easy to assume this is just a small business problem. MSMEs are stressed, they lack engineering staff, so they fail. But if I am a giant corporation, a massive multinational steel plant, or a huge cement manufacturer, I have an entire department of highly paid electrical engineers on staff. Surely the mega corporations have this figured out?
That is the logical assumption. But C.A. Mahavir Kumar's data refutes it beautifully. The report doesn't just look at the MSMEs. It includes an analysis of the ultra-high power consumers as well. These are massive industrial facilities with 10,000 kVA up to 60,000 kVA contract loads.
We are talking about companies spending anywhere from 100 to 200 crores annually on electricity alone, hundreds of millions of rupees. They absolutely have the budget for a dedicated technical team.
They do. And you would expect their power factor to be locked in a perfect 0.999 year-round. But the empirical data reveals a completely different reality. While the absolute largest mega consumers, those in the 40,000 to 55,000 kVA bracket, manage to keep it relatively stable, the consumers in the very heavy 10,000 to 35,000 kVA bracket show massive costly inconsistencies.
How so? What does the data show?
The report analyzed the standard deviation of their average power factor over the 11-month period, as well as the absolute variation between their minimum and maximum recorded power factor. And the results are wild. Even at these ultra-high load levels, with teams of engineers, the data shows huge maximum fluctuations. Their efficiencies bouncing up and down wildly, repeatedly dropping them straight into the MSE-DCL penalty zones.
Wow. Okay, so if I'm understanding this correctly, this fundamentally changes our diagnosis of the problem. If an ultra-high load consumer spending 100 cores a year with a dedicated engineering team struggles to maintain a consistent power factor because of capacitor degradation and complex load fluctuations, how on earth can a stressed, under-resourced MSME owner rely on a static, sell-and-disappear gray metal box?
This raises an important question, doesn't it? If even ultra-high load consumers with dedicated technical teams struggle to maintain consistent PF, how can an MSME rely on static hardware? They absolutely cannot. The data proves it conclusively. Static hardware is structurally incapable of solving a highly dynamic physical problem over a multi-year horizon. It doesn't matter how big your factory is. Unmonitored hardware guarantees failure.
All right, this is the perfect pivot point in our deep dive. We have meticulously diagnosed the symptom, the massive margin-crushing utility penalties. We have found the structural bottleneck, unmonitored, thermally degrading capacitors sold by vendors who immediately abandon the site. And we have seen the massive scale of the problem in the MSE-DCL dataset, proving that this is a multi-core bleed across the entire industrial sector. So how do we actually fix the control point?
This brings us to the strategic notes on restorative engineering and edge AI. The thesis proposed here is simple, but it represents a profound paradigm shift in industrial maintenance. We have to fundamentally stop our reliance on unmonitored hardware. The solution to this crisis is not for a lab somewhere to invent a slightly better capacitor. The immutable laws of physics and thermodynamics dictate that any physical capacitor will eventually degrade under heavy, relentless industrial load.
Right, you can't out-engineer thermal stress forever. The dielectric film will eventually break down.
Exactly. Therefore, the solution is to shift from static hardware to actively managed infrastructure. The strategic notes propose a highly specific mechanical and software reality to achieve this: the Edge AI kVAh monitor.
Let's break down what this actually looks like physically on the factory floor, because I want to be clear to anyone listening. We are not talking about some delicate, consumer-grade smart home device that you tape to a wall.
No, absolutely not. The physical specifications of the hardware are critical to its success. This must be a ruggedized, heavily shielded industrial-grade monitoring unit. It has to be housed in an IP67-rated cast aluminum enclosure.
For those not familiar with industrial specs, an IP67 rating means the device is totally, completely dust-tight, and it can literally survive being submerged in a meter of water. It is essentially bomb-proof.
It has to be. Think about where this device lives. It is going to be mounted directly adjacent to the main electrical inlet deep inside a factory. It has to survive relentless, conductive metallic dust floating in the air from manufacturing processes. It has to survive extreme ambient heat in an unair-conditioned electrical room in the middle of an Indian summer.
Yeah.
It has to endure the continuous bone-rattling low-frequency vibration of heavy machinery operating 50 feet away, and it must operate silently and flawlessly for years without drawing any attention to itself.
Okay, so we have an indestructible aluminum box on the wall. How does it actually get the data? Because here's a hard truth about factory owners. They despise downtime. If you tell an MSME owner that you need to shut down their entire production line for a day to splice a bunch of complicated sensors into their main high-voltage feed, they will kick you out of their office.
That is the most elegant part of the hardware design. It is entirely non-disruptive. Let's look at two scenarios. First, imagine the factory has a relatively modern APFC panel. It's failing, it's unmonitored by the vendor, but its internal computer is still generating basic data. In this case, the Edge AI gateway simply intercepts the data using standard industrial communication protocols.
Protocols like RS-485 or Modbus.
Exactly. For those unfamiliar, RS-485 and Modbus are essentially just the standard universal languages that industrial machines have used to gossip with each other for decades. The AI gateway plugs into the existing data port and just quietly listens to the raw data stream the panel is already generating, but failing to act on intelligently.
Okay, but what if the factory's older? What if the APFC panel is just an ancient, dumb box of mechanical relays from 20 years ago with no data port at all?
In that case, the gateway utilizes non-invasive current transformers, commonly called CT sensors.
I love CT sensors. Explain how these work, because it feels like magic.
They are brilliant. A CT sensor is essentially a split-core ring. It opens up like a jaw, you don't have to cut any thick copper wires, and you don't have to shut down the main power feed. The technician simply snaps the ring around the outside of the thick incoming electrical cables. As the alternating current surges back and forth through the main cable, it naturally radiates a magnetic field outward.
Okay.
The CT sensor simply measures the fluctuating strength of that magnetic field through the insulation, and from that, it can perfectly, instantly calculate the raw, active, and apparent power flowing into the factory. It clips on in 10 minutes, safely, with zero factory downtime.
Okay, so the gateway is installed. It is ruggedized. It is securely capturing the high-resolution, millisecond by millisecond data of the factory's power draw. But here's where I have to push back. Capturing a mountain of data is one thing, but how does this actually solve the mechanical degradation of the capacitors? Putting the beautiful graph on an iPad screen doesn't fix a broken piece of dielectric film inside a gray cabinet.
This is exactly where the Edge AI component changes the paradigm. The monitoring unit isn't just acting as a dumb pipeline streaming raw data up to a cloud server for some human analyst to look at next month. It runs a highly specialized, lightweight predictive AI model locally, right there on the Edge Gateway's internal processor.
Why locally? Why not use the infinite computing power of the cloud?
Two critical reasons. First, industrial factory floors, especially inside thick concrete electrical rooms, often have terrible or non-existent internet connectivity. You cannot rely on a constant 5G connection. Second, you need zero latency decision-making. The local AI model tracks the precise degradation curve of every single capacitor bank in real time. It analyzes exactly how much reactive power is being demanded by a heavy motor turning on versus exactly how much leading reactive power the APFC panel successfully injected a millisecond later.
Going back to our canal boat, the AI is constantly monitoring the angle of the tow rope and instantly measuring exactly how hard the rudder is pushing back.
Yes, and because the AI is tracking this historically, it builds a degradation profile. It learns that capacitor bank number 3 successfully delivered 25 kVAh in January. By June, it observes that bank 3 is only delivering 22 kVAh for the exact same command. It plots that specific thermal breakdown curve.
And it projects it forward.
Exactly. It extrapolates the curve into the future. It predicts, with high mathematical certainty, the exact day that the total system capacity will degrade so much that it slips below MSEDCL's strict 0.90 penalty threshold.
Here's where it gets really interesting. Hardware degrades in the background, inevitably, invisibly. But the software verifies the physical reality. It completely transforms the APFC panel from a dead fire-and-forget metal box into an actively managed, living piece of infrastructure. It's like having a system that tells you your brake pads are going to catastrophically fail next Tuesday before you ever hit the tree.
Precisely. And from a strategic business perspective, it shifts the entire control point of the industry. The entity that holds that real-time predictive data stream regarding the facility's reactive power now owns the relationship with the facility.
Which perfectly sets up the business reality. It is one thing for an engineering team to sit in a lab and build a really cool IP67 Edge AI monitor. It is another thing entirely to walk onto a loud factory floor and convince a highly skeptical, deeply burned out MSME owner to adopt it. Think about their psychology. These owners have already spent lakhs of rupees on traditional vendors who promised the moon and then vanished, leaving them with broken panels and massive utility fines. Why on earth would they trust a new tech startup walking in talking about edge AI and predictive degradation?
The short answer is they won't. They will not trust the technology, and you shouldn't ask them to. They will, however, trust the economics. This is where the business model of restorative engineering has to fundamentally shift away from everything the incumbent vendors do. The startup cannot operate as a hardware seller. They must operate as a continuous aligned energy partner. They aren't selling a gray box, they're selling a financial performance guarantee.
Okay, walk me through the mechanics of that. How does that look on paper for the skeptical factory owner?
The economic proposition for the MSME is designed to be completely irresistible. Zero upfront capital expenditure. Zero CapEx.
Wait, the startup walks in, provides the bomb-proof IP67 aluminum gateway, provides the highly sensitive CT sensors, pays for the technician's installation time, and provides the local AI predictive software completely for free.
Yes. The installation is 100% free. The startup absorbs the hardware cost and the installation risk entirely. The factory owner doesn't write a single check to get the system online.
Okay, I am a huge fan of free infrastructure, but how does the startup survive? How do they make any money to cover their hardware costs, let alone scale a business?
Through the monetization engine of the kVAh arbitrage, remember the 25% profit leak we talked about, the massive penalty fines the factory is bleeding out to MSEDCL every single month. The startup's business model is to take a 20% residual cut of the eliminated utility penalties every single month on an ongoing basis.
Oh, wow. Let's run the math on that to make it concrete. Let's say our auto parts factory is currently paying a massive Rs 100,000 fine and penalty to the utility company every month because their power factor is at a dismal 0.85. The startup installs their Edge AI system for free. The system actively manages the hardware, fixes the lag, and drives the power factor up to 0.99. The MSEDCL penalty on the next bill drops to absolute zero. The factory just saved Rs 100,000.
And out of that newly found Rs 100,000, the startup sends the factory an invoice for Rs 20,000.
So the startup gets a healthy recurring revenue stream, and the factory is still up Rs 80,000 a month in pure profit compared to where they were the month before.
Exactly. It is a perfect alignment of incentives. The vendor only gets paid if the facility's power factor remains near unity. They only earn revenue if they successfully eliminate the regulatory tax.
But let's stress test this, because we just spent the last 30 minutes proving, with physics, that the capacitors inside the panel will inevitably degrade. Thermal breakdown is unavoidable. So 6 months into this contract, a capacitor fails. What happens to the startup's revenue?
This is the operational beauty of the predictive system. The local AI model sees the degradation happening. It flags that capacitor bank number 3 is going to drop the total system efficiency below the utility threshold next Wednesday. The startup's operations dashboard receives the alert. The startup proactively dispatches a field technician. They drive to the factory on a Tuesday, open the panel, and replace the failing $50 capacitor component before the monthly utility billing cycle ever closes.
They are fixing the plane while it is flying.
Yes. By proactively spending $50 on a consumable component, they protect the factory from suffering the massive MSEDCL fine that month, which simultaneously protects the startup's own Rs 20,000 recurring revenue cut. The startup is financially incentivized to maintain the hardware perfectly, forever. The sell and disappear model is replaced by a monitor and maintain model.
I love the elegance of that. It takes the risk that was externalized onto the factory owner and places it squarely on the shoulders of the entity that actually has the data and the expertise to manage it. But I have to push back a little on the budget gravity here. We talked extensively about how financially stressed these MSMEs are post-COVID. Even if the startup walks in and says zero CapEx, a skeptical factory owner is going to look at a projected new Rs 20,000 a month invoice and say, look, I love the idea, but I absolutely do not have the budget to add a new SaaS software service to my ledger right now.
But they do have the budget.
Mm-hmm.
That is the genius of explicitly targeting the regulatory penalty. The budget comes entirely from the OPEX, so the operational expenditure that was previously allocated to paying MSEDCL's utility penalties. The factory's accounting department was already cutting a check for that 100,000 rupee penalty every single month. It was already baked into their overhead assumptions.
Yeah. I see. You weren't asking them to find new money. You weren't asking them to increase their operational budget. You were simply intercepting and redirecting the money they were already throwing into the furnace.
The product funds its own scale out of thin air, or, more accurately, out of eliminated taxes. It is a pure arbitrage play.
This all sounds incredible in theory. It's a perfect closed-loop system, but the strategic notes outline a very specific challenge: actionable validation. How does a startup actually prove this invisible leakage to a factory owner in the real world? If an owner has spent years just grumbling and paying the high utility bill every month without questioning the complex physics of reactive power, how do you get your foot in the door to even offer the zero capex model?
The strategic notes outline a highly engineered 48-hour validation plan to overcome exactly this psychological barrier. Step 1 is crucial, and it requires discipline from the startup. Do not try to sell a massive facility-wide system up front. Do not walk into the owner's office with a 40-slide pitch deck about edge computing, neural networks, and dielectric breakdown. Measure the leakage first.
Show, don't tell.
Exactly. Step 2. You ask the owner for permission to conduct a risk-free audit. You install a single, extremely low-cost version of the edge monitor on their main incoming line. The notes suggest this stripped-down hardware might cost the startup maybe $50 to build. You clip the CT sensors onto the main feed. As we established, it takes 10 minutes. There is absolutely no downtime for the factory.
And then what? You just walk away.
Step 3. You walk away and let the system run for exactly 48 hours. You want it to capture 2 full normal production cycles. You let the AI quietly record the high-resolution data, the exact millisecond gap between the true active power, the kW, and the apparent power, the kVAh. You capture every single instance of leading and lagging reactive power as their massive stamping presses and cooling fans cycle on and off.
You capture exactly how far off the path the horse is pulling the boat in real time?
Yes. Step 4. You return to the owner's office after 48 hours. And this is the critical moment. You do not present them with complex standard deviation charts. You do not show them R-squared values or talk about thermal dynamics. You present them with a single, undeniable metric. You show them the exact, literal monetary leakage they suffered over the last 2 days, purely due to their degraded, unmonitored capacitors.
You show them the pile of cash burning on their factory floor.
You extrapolate that 48-hour loss over a 12-month calendar year. You show them the massive annualized total. And then, in the face of that indisputable financial pain, you offer the zero capex shared savings arbitrage model. This execution perfectly satisfies the fundamental rule of competitive asymmetry in modern business.
Remind us what that rule is.
The entity that holds the real-time data stream of the facility's reactive power owns the control point and the relationship with the facility. Once you show the factory owner the invisible leak using your proprietary real-time data, the incumbent sell and disappear hardware vendor looks entirely obsolete. They look negligent. You own the relationship because you are guaranteeing a financial outcome, not just pushing a metal box.
Okay, let's take a step back and recap the incredible scale of this journey. We started by looking at what seemed like a simple, almost boring bureaucratic shift by MSEDCL, changing a billing formula from kVAh to kVAh. But by digging into the math and the physics of alternating current, we saw how that single regulatory change created a multi-core nightmare for the MSME sector, essentially taxing them ruthlessly for the necessary physics of their heavy machinery.
Right. We examined how the market's default response. The panicked buying of static APFC hardware completely failed because incumbent vendors abandoned their clients. They left factory owners victim to the inevitable thermal degradation of capacitor banks. The risk of complex mechanical failure was entirely unfairly externalized onto MSME owners who were structurally unequipped to monitor it.
And finally, we unpacked the brilliance of the restorative engineering solution by pairing a ruggedized IP67 Edge AI monitoring gateway with a recurring shared savings service model. A startup can completely neutralize the threat. They intercept the data, predict the failure, swap the $50 part before the penalty hits, and share the savings. They transform a dead, failing metal cabinet into an actively managed, highly profitable energy partnership. It is an absolute masterclass in finding a hidden bottleneck, understanding the physics behind it, and completely capturing the control point through aligned incentives.
It truly highlights the immense value of critical thinking in industrial business. It is about looking past the visible symptom, which is just a frustratingly high-power bill on a desk, to find the actual structural bottleneck, which is unmonitored degrading hardware. Once you truly understand the mechanism of the bottleneck, entirely new, highly profitable business models become obvious.
And that brings us to a final provocative thought for you to ponder as we wrap up. We just spent an hour meticulously dissecting how static APFC panels are quietly degrading in hot basements, acting as a massive silent tax on factory margins simply because nobody is watching them. So I want you to look at your own industry. What other expensive, unmonitored, set-it-and-forget-it hardware is currently failing in the background right now? What else is just sitting there in the dark, bleeding profit, waiting to be turned into a massive recurring revenue software solution by someone who simply decides to put a sensor on it and measure the leak? Think about it. We'll see you on the next deep dive.